Welcome back to astronomy. We are continuing digitally regardless of any issues that have been going on with the school closures. So just listen closely to this intro because this contains all the key details of what you're going to need to be doing over the next few weeks, including what we're doing for today's activity. For today's activity, we're hanging out in my garage and we're going to do some astrophysics with our gravitational well that I jacked from the school. So hang in there and let's continue forward. Before we go too much further, I just want you to know what the district's expectations are and what my expectations are. The district will post new materials every Monday to the district website, and I will also put them on our class website. Our class website is now a Google Classroom, so you do not need to access my Google site anymore. You need to go to my Google Classroom. That is at tinyurl.com/ all caps THS uncaps Astro. So tinyurl.com/ THS Astro. I forgot for a second. So I will be posting new materials and the district will be posting new materials beginning Monday, April 13th. Different days of the week have been designated as different subject days. So make sure that you are looking at the website to see which days you should be working on what materials. Technically, you can work on any of it, any day of the week once the materials are released, but certain days of the week, which I will put up to the side of the video, different days of the week have been designated for different subject materials. For our class, it is a science class, so Wednesdays are the designated days for astronomy. Again, you can complete these materials beforehand or after, but Wednesdays are the designated astronomy days. And what that means is Wednesdays is when your science teachers will be available to conference with you digitally. So if you need any help with a science class, Wednesdays are the day to do that. And I will be available all day for that. Any questions you have, feel free to reach out to me through email or through Google Meets. I'm going to be posting a new Google Meet to my website every day so that you guys can know where you can meet me when the time comes. But if I'm not active on that chat or whatever, just make sure that you send me an email because I'll be checking it frequently. Again, materials will be released Monday, but Wednesdays are the designated days to get help with my class. So Google Meet is when we're going to be doing that. And Wednesdays, technically my office hours are from 8 to 3:30. So you can get to me basically any time that day, but Monday, Tuesday, Thursday, Friday, I will also be available. Just make sure you reach out to me. The way class is going to operate is Mondays materials will be released. Wednesdays, I will be specifically available to help you, but your assignments are never due until the following Wednesday. So Monday, April 13th is when this video will be released and you'll have access to the first week's materials. But Wednesday, April 22nd is when all of this first bit of information is due. So make sure that you're watching the website for that information, for those updates, and to see specifically what you need to submit. So this week, there is a lab packet available on the website, again, tinyurl.com/ THS Astro. That lab packet is going to go along with a video. I'm going to be using the gravitational well set up in my garage to guide you through a lab packet that I was hoping you'd be able to do individually, but hopefully I do a reasonable job showing this for you as well. You're welcome to set this up in your garage, in your house, or whatever, just using like a hula hoop and a piece of fabric, but you know that I've got the optimal materials, so this video might serve your purposes a little bit better. For this week, no matter what type of student you are, concurrent or non-concurrent, you will need to complete a quiz. The quiz for all students will be your primary grade for the week. If you have any other questions, remember, please feel free to reach out to me at any time during the week, even though Wednesdays are the best days to do so. With all of that considered, I would encourage you to reread any emails that I've sent you, rewatch this intro to the video to make sure that you are aware of exactly what your responsibilities are as we continue digitally. There will be 6 weeks of material. We're going to spend 2 weeks on the gravitational well. We're going to continue into some space travel, some special relativity, the Big Bang. It's going to be good stuff. So hang in there and let's get started. I hope you're all doing well. First things first, I want anybody who wants to be able to try to build the gravitational well at home to be able to. So just in case you want to try and run these experiments yourself, ideally what you have is a bunch of binder clips or clamps to attach to the edge of this material. So the gravitational well altogether just basically looks like a trampoline. If you had a trampoline itself even works. But what I've got is a bunch of spandex that I got from Joann's attached to a giant PVC pipe frame. There's all these different DIY versions of this that you can find online. So if you're looking to purchase one of these or to really build an authentic one, just look online for more details about the specifics for how you cut the PVC pipe and how much spandex you might need. But again, this is relatively simple. And what you're going to need is you're going to need the gravitational well itself. So spandex to attach to some sort of frame, and then also some clamps to hold it on there. I've got all of these sitting on chairs to make a relatively stable surface. But with that, there are also budget versions that you can do. The spandex is low friction, which is nice, but you can use blankets. I've even seen examples where people just take a dish bowl, so something you would eat out of, and they stretch saran wrap over the surface, and then they can put things in the middle. And that makes for a nice little version that you can use as well. But just so you know what's going on with the gravitational well and some background information before we actually get started, is we did a lab regarding this early in the year, and we were talking about exactly what's going on with this. At this point, you're going to want to complete your engage portion of the week's activities and the pre-lab. So go ahead and pause your video and complete the pre-lab and engage sections of your lab packet. This makes up the first 2 pages. So let's get some background information on what the gravitational well is. The gravitational well, as emphasized in your pre-lab, is a representation of space and time, the fabric of space-time as stated by Einstein's general theory of relativity. We had all this missing information with Newtonian physics. Newton said that masses pulled on each other, but he had no explanation for how they pull on each other. They weren't connected by giant ropes, at least not observably. So like, what exactly is causing these things in space, like the Earth and the Moon, to be attracted to each other? If we think about space as basically a 2-dimensional fabric here, we know that space-time is actually 3-dimensional, but for our analogy, we're going to be talking about it as 2-dimensional. With this 2-dimensional fabric, you're going to notice that I've got it relatively flat right now. We are moving on to part 3 of the lab. So with space-time sitting here in front of us, let's think about what happens if we add an object to that surface. And you might even want to just take a second to pause and think about how straightforward that is. If I was to put something in the middle of my trampoline, what's going to happen? It's going to distort. So here I've got some objects of varying size. If I was to take something like a marble, for example, and put it on the fabric, that marble technically is depressing space-time a little bit. But the thing is, it's just a marble. It can't do much damage to space-time itself. So let's replace that marble with something a little bit bigger, like a billiard ball. Billiard balls are relatively dense, and therefore it depresses space-time a little bit more. If we were able to add something much more massive, I don't want to break the thing in the middle here, but say I was to jump in the middle of that, we would get a big depression. Here I've got basically a marble apple. This thing's pretty hefty, and if I put that in the middle, you could even observe that it's more massive because it greatly depresses the gravitational well. So here we've got some things of different masses, and we're seeing how they depress this all a little differently. So we've seen how that is occurring. But let's say that we take 2 things of relatively equal mass. I've got a racquetball and I've got a golf ball. The racquetball and the golf ball, they weigh about the same, but looking at number 1 in part 3 of the lab packet, we're under A, general observation. If you haven't had a chance yet, look at number 1. It says to gather a variety of masses, place them on the rubber sheet, or our space-time analogy here, and describe what happens. We saw that if the mass increases, we get more of a distortion in space-time. We are actually warping space, and that warping is what's responsible for that gravitational pull. If we were to take 2 things of equal mass, like golf ball, racquetball. They weigh about the same. And I was to say, like, let's increase the radius of the object. So the racquetball obviously has a greater radius than the golf ball. So with the golf ball in the middle, let's get right up in it. You can see a slight depression, and I'll go here for a reference angle. But let's replace that with the racquetball. With the racquetball there, you'll notice that the depression is not significantly deeper. But the thing is, with a larger radius, that distortion is spread out over a larger distance. So when we have different radii, but the same mass, really just the area of influence and the intensity of that gravity locally is slightly changed. Part C says that we have more than one object located on the sheet. I think you're going to see this as pretty straightforward. Let's grab two golf balls. I'm going to put one over here. See if I can get it to stabilize. I'll just let it roll until it finds a nice happy place. Fair enough. Okay. So again, shouldn't be rolling. In space-time, things don't roll by themselves. They don't attract themselves. But I don't have a totally flat surface here. So, golf ball settled out. Let's add another object. So those two objects both depress the sheet. I think what I'm aiming to show here will be a little bit more obvious if I was to take something massive like the billiard ball. And then let's add the golf ball right here. When I let go of the golf ball, observe what happens not only to the golf ball, but to the billiard ball. They pull on each other very slightly. So I'm going to zoom in here. Watch the billiard ball as the golf ball approaches. The billiard ball is not nearly as affected by the distortions in space-time as the golf ball because it has less mass. So technically the golf ball is pulling on the billiard ball, but it's an insignificant amount because of all of this. So part D, one at a time, place two objects of equal radius but varying mass in the center of the sheet. So we want equal radius, varying mass. For this part, I'm going to actually go ahead and get us set up on a ladder back here because this is my budget tripod. Nice. Okay. So, question 1, part D says to take two objects of equal radius but different mass and place them on the rubber sheet. So the billiard ball and the racquetball, they're about the same size, but obviously the billiard ball is going to weigh a little bit more. It's made of a heavier material, and the racquetball is hollow, so it's obviously not going to have much mass to it. So if we take the two and we put them on the sheet at the same time and we let go, you may have noticed that the billiard ball itself moved towards the racquetball. Even though the racquetball is significantly less massive, you're going to notice that difference in mass. The more massive object is going to pull harder on the less massive object. So when I let go, it makes sense that the low mass object rolls towards the high mass object. At this point in the lab, I want you to pause the video and answer questions number 2 and 3. They pertain to your pre-lab and some of our conversations here. So, pause the video, answer questions 1, 2, and 3 in part A of the lab. Some of you may have been absent the first time we played with the gravitational well, so one more piece of background information is to think about what an orbit is. We know that if we have a massive central object, so this apple, the marble apple, the really heavy thing, is going to act as the star in this scenario, the center of our solar system. So this is our sun. I'm going to place it roughly in the middle of the gravitational well, and I'm going to take some less massive objects and interact with them here. So take a second to guess what's going to happen when I let go of this golf ball. Wow. It rolled to the center because we had a gravitational depression. This gravitational well attracts other things towards it. Technically, we know that the golf ball exerts its own distortion on space-time, so it moves the apple even slightly. But if I just let go of the golf ball, the most obvious motion is going to be towards the apple, towards the sun. The planet is rolling towards the sun. We know, fortunately, that our planets don't roll straight into the sun. So, using a golf ball again, just think about what's different between this golf ball being the planet in an orbit. What's the difference between this, just a planet sitting stationary in space, and an actual orbit? What did I have to do to that golf ball to make sure that it didn't fall straight in towards the apple? You could have even seen me physically do it when I started the experiment. If I take a planet and it's sitting stationary in space, the only acceleration it experiences is inwards. It falls straight in towards the apple. But if I throw the ball sideways, it's still falling towards the apple. The apple is sitting in the middle, holding it into this fabric. And as a result, the golf ball swirls around as that central force, the central gravity, keeps it rolling in the well, but it's falling sideways faster than it's moving down. So technically, like the International Space Station, the Earth, they're being pulled inwards, but they move faster sideways than they do inwards. And just to demonstrate that again, if I was to throw that golf ball sideways at exactly the same speed, with no central force, it runs into the edge of my space-time well, and it's now just behaving randomly based on the tilting of the floor. But I'll do it with a little more speed, because if there's no central mass and I throw it sideways, it just falls off the gravitational well. To be bound to a stable orbit, the golf ball needs a defined sideways speed to keep it in orbit around the central object. So the planet needs to be moving sideways at a specific speed to be going fast enough to avoid falling into the star. Notice if I just barely push it sideways, it didn't go fast enough. It was falling towards the star faster than it was moving sideways. At this point in the lab, you should be able to complete the entirety of Part A. So please take this time to finish Part A. We finished by discussing number 4, what makes a stable orbit? So Isaac Newton had his law of gravitation. He was able to describe the way that different objects with mass would move around each other and exactly how hard they would pull on each other. And this has helped Galileo discover planets. I think it was Neptune that was discovered entirely by calculation. The ideas behind this, like his math worked, but it missed the mechanism by which these objects pull on each other, and that's where this gravitational well comes into play. Einstein said that they don't pull on each other using ropes. It's not a string that these two objects are bound to and they rotate around as a result. It is just a distortion of the fabric of space-time itself. So our three-dimensional space is warped and things roll around in that well. So that's all neat and dandy. As soon as Einstein put this out, all of a sudden Mercury's orbit made sense. All these other weird phenomena that we were observing in the universe, we could explain them. So mathematically, Einstein's general theory of relativity, it's looking pretty tasty. The thing is, how do you prove it? We live in 3 dimensions, and Einstein is saying that those 3 dimensions themselves are distorted. When we look at the sun, we don't see a big flat and then depressed well as something comes in and then sinks space-time. We don't see that distortion. So how do you verify this? He's a smart guy. So he was thinking, Well, if space itself is curved, then anything that is following a trajectory through space should abide by that curvature. There are things in space, such as photons, that don't even have mass. But because they're moving through space, they should follow the curvature of space. And that brings us to part B of our lab. Take a second to look at number 1. Number 1 asks, if you're actually going to warp space significantly, what type of object do you need? I want you to think about some of the larger things in space. If we take the moon, we know that the moon's gravity is significantly decreased. So its space-time depression, its gravitational well, is significantly less than that of Earth. That might be the equivalent of putting like a marble on here. A pretty much negligible mass in the context of my gravitational well. The Earth, maybe that's like putting a few marbles on. It's got more mass, but it's not still a significant depression. What have I said am I putting in the middle of this gravitational well? What does this apple represent? It represents the sun. So stars and objects bigger than stars, they're going to make significant depressions that they really mess with the curvature of space-time. So with that in mind, let's look at the next portion of this lab, number 2. Number 2 says that we want to set up a gravitational well with a large central mass. We have that. We've got a star sitting in the middle, and then we're going to take something with no mass. Of course, I can't do that, but I've got some small marbles, and these marbles will suffice because relative to the apple, it's pretty much negligible. So when this marble is going to serve as a photon, we're going to roll it past, and we're going to see what it does. I'm going to roll it with sufficient speed because we know that photons move at the speed of light, 670 million miles per hour, or 300 million meters per second. So if I take this marble, and if I roll it rapidly past this apple, watch what happens. Whoa. Let's do it again. So, watching once again, watch the path of the marble. Did it move in a straight line? It didn't. I'm going to take this string and I'm going to model the path that I saw this photon follow. So I started about right here. Ignoring any squiggles, assuming this yarn goes in a straight line. It followed a path roughly like this. I'm going to make a little adjustment here just so this is a little bit more straight, but it followed a straight path in. I made a little adjustment here to straighten it all out, but the photon followed a straight path in, space-time was distorted and caused the photon to curve onto a different path. So this is the origin of our photon. It's just light flying through space, right? So the light flying through space moves towards this object, follows the curvature of space-time, and then leaves. We notice that the string goes off in a different direction than when it once came, than where it came from. So let's think about the next portion. At this point, you should be able to answer question 2A. We laid the string on the gravitational well, and we showed the path of the photon, and we can see the path it followed. If you haven't answered it yet, pause for just a second and release that answer. I want you to think about this. Over here was the source of my photon, and back here is where the photon ended up. So the source of the photon versus the actual location of the photon, or the path the photon followed. I want you to think about if the photon originated on the camera side right here, but I, as an observer, am looking over here. From my field of vision, if I was to point at the origin of the string, the origin of the photon, it's actually behind the apple. If this was the star sitting in the middle of our solar system and I wanted to see the star that created the light, so let's say this photon that I threw across the well, its path is modeled by the string. Let's say that this came from a star. This was a photon emitted by a faraway star. That photon originated behind the sun. If I was to try and see that star, I couldn't. It's behind the sun, and you know that looking at the sun is a bad idea. So we can't see that. But the thing is, as an observer, does that light still reach me? Yes, it does. That photon originated from a star that was kind of going off path. But notice now, if I'm the observer on Earth, I can still see this string nonetheless. And if I can see this string, I can see the star. But the star is located behind the sun. Isn't that crazy to think about? So I want you to think about, as the observer, where does it look like this light came from? I know that the star whose photon I was able to trace is actually behind the star. But if I look at where this came from, and I look straight along where this originated, I want you to think about the apparent position versus the actual position of the photon source. So, with this in mind, I'm going to hold my hand up, and I'm going to block a portion of this photon path from view, because the observer, you or the people on Earth looking at this star, they're back there. But if I was to, so I have blocked the portion of the light that was behind the star. If you are an observer standing right here, looking at where this light came from, think about where you think the light came from. You would imagine the light followed a straight path through space, right? So this right here looks like it would have originated, if I was to follow that line, this is tricky. If I was to follow that line, that light, if it was to follow a straight line, looks like it would have originated over here. But the light actually originated here. So we would actually see the star in a different position from where it actually is. The light from the star leaves in all directions, technically, leaves in all directions from its source, is distorted by the path of the sun, or distorted by the gravity of the sun, and curves around the sun for us to see it. This is how Einstein was going to scientifically and experimentally verify his ideas. We're now looking at number 2C of part B. Number 2C of part B says Einstein ran this experiment except in the real world. If he was going to prove this is true, he can't just put an apple in the middle of a trampoline. He's got to actually show it. So he saw that light from a distant star curved around the sun and into the view of people on Earth. This star is technically from that field of view. That star is behind the sun, so how can you see that star? So he deliberately conducted an experiment where the light from the star should actually curve around the sun. He conducted this experiment on May 29th of 1919. I want you to Google this date and note what event took place. Why did the experiment need to take place on this type of day? Why did Einstein need to conduct this experiment to see the light of a star behind the sun on this day? Pause the video, Google it, and go ahead and answer it. So why did Einstein need to conduct his experiment on May 29th of 1919? Think about it. If I'm an observer and I want to see the star behind the sun, think about what's going to happen if I look back to the other end of the string then. If I'm right here and I'm looking back at the other end of the string, what's in my way? The sun. Okay, well the light curves around the sun. It's next to the sun, it's not behind the sun. Oh, perfect. So I'll just look at this and blind myself because the sun is in the way. Maybe that light is slightly off to the side of the star. It looks like it's coming from over here, but the sun is still in the way nonetheless. So I can't look at the star next to the sun unless the sun's light is blocked out. Otherwise, it's too bright for me to see. You don't see stars during the daytime. You try to look at the sun, don't, you're going to have a bad time. So, during that solar eclipse, the stars came out. Enough of the sun's light was blocked that we could see the stars next to the sun. So, if solar eclipse happens and it blocks out that light from the star for me, then I can see to the side. At this point, I've removed the string because what I was showing was the path of a single photon. Do stars emit a single photon, a single point of light? No, they don't. They release an infinite number of photons in every direction from every point of the surface. So showing the path of a single photon, it's representative for a distant star where it looks like we're just getting a single point of light. But let's think about what's actually happening. I've got my object in the middle, whether this be a star or a galaxy or whatever, and I'm going to put my photon source, another star's light, or maybe even another galaxy's light, I'm going to throw all that light towards that other galaxy, or towards that star. So, for the intents and purposes of this next little bit, let's say we've got a galaxy. The apple now represents a galaxy in the middle of this gravitational well. If I take the light from a star, and I throw it in every direction, just like a star actually would, because photons are released in every direction. Let's use these marbles. If I take these photons and just throw them towards this apple, throw these pieces of light towards a galaxy, watch what happens. Stars are not emitting a single photon. They're emitting photons in every direction. So let's try throwing some photons in different directions. Similar to the first experiment, I'm going to throw this marble, or our photon, past the galaxy in the center, just at a reasonable speed so that it's going to swing around and bypass this thing. We saw it follow a curved path. Let's go ahead and lay out the string for that. What I've got shown here is probably not the perfect path that you saw, but it's curved nonetheless, correct? So, that was a photon being sent off slightly to the right side of this apple here. But let's try throwing a photon off the opposite side. I'm at a string. So let's just think about what we saw. If I was to trace the path of the photon I saw, the photon went out this way, around the star, and ended up nearly in the same position as that other photon followed. So, technically, I don't just have this path of the photon. I have another path that looks somewhat like that. If I've got strings going on both sides, if that photon bends around both sides of the galaxy, then technically, as an observer looking towards that galaxy, I see the light from a star behind the galaxy on both sides of the galaxy. I'm seeing the same image of a star twice. I'm seeing the photons that went around this way, and I'm seeing the photons that went around this way. That is a concept called gravitational lensing. Just like looking through a fishbowl or through some glasses, you'll notice that images get a little distorted. If you've got a glass sphere, that's a perfect example of showing how the light warps around, even in a water bottle, because it's kind of cylindrical and curved. You see that light bending around inside the water. So if we're looking towards this galaxy, any light that just barely misses that galaxy, that's coming from that central source, is going to be bent around and back into our eyes. Again, it's going to be bent around and into one location. So you will see multiple images of the same thing. I would highly encourage you guys to look up a picture on Google of gravitational lensing. If you think back to the movie Interstellar or images of black holes, what you see is the light being bent around the black hole. At this point, we have finished part B of the lab. So, any questions that you may have been missing, make sure you pause now and go back and answer anything that you may have missed. Part C is about 3 different concepts that are all interconnected because they're all unified under the general theory of relativity. Part C is about escape velocity, black holes, and gravitational waves. The only subjects that you're going to be held accountable for are escape velocity and black holes. Those of you that are interested, gravitational waves, massive breakthrough, proving Einstein correct 100 years after general relativity was first discovered. Gravitational waves are this idea that ripples in space-time, because of shifting objects with massive gravitational wells in space, like they move around each other and they create big bounces. It's the equivalent of me jumping in the middle of this thing. That was proved 100 years after using amazing technology. He predicted them using mathematics 100 years in advance, which is extremely impressive. Escape velocity, black holes. So escape velocity, just think about the word itself, escape velocity. Escape means to get away from. Velocity, that deals with speed. Velocity and speed, for the intents of this assignment, you can think of them as the same thing, even though velocity is technically a vector. It has magnitude and direction. So speed, escape speed. How fast do I need to go to get away from something? You'll notice that if I throw marbles at varying speeds towards my star here, we'll say the apple is a star. Apple is a star. If I throw marbles towards the apple, sometimes they get stuck. Sometimes they don't get away from the well. If I throw it in a light circle around the edge, you can see that marble rolling around in a circle. It can't get away. And as a result, it starts orbiting. Escape velocity, though. Escape velocity is the minimum speed at which an object with mass can escape the central object. Think about the fact that I've got this marble apple in there right now. That's making a pretty significant dent in my gravitational well. Is that going to be easier to get away from or harder to get away from than if I put a golf ball in the center? A golf ball won't depress the sheet as much. It doesn't have as deep of a well. It's really easy to get away from, whereas this apple, you can see a bunch of marbles sitting in the center right now. Like it's holding them there. So escape velocity is the minimum speed required to escape this apple. You'll notice that if I don't throw it sufficiently hard, that one almost got away. It was approaching its escape velocity, but it wasn't going quite fast enough to actually get away. So I'm going to try several times to roll a marble at a speed at which it barely gets away from this star. It escapes its gravitational influence. If I throw it super fast, if I'm going the speed of light like an actual photon, it's going to go quickly. So I'm going to use a golf ball. If I throw this rapidly, the photon, speed of light, that thing was by no means captured. But if I roll a marble at just the right speed, I'm going to throw it at varying speeds again, so that it just barely escapes. Ooh, that was a good one. So the path that followed, it moved. I recognize I might not be laying this out quite perfectly, but it followed this path. If we think about the idea of escape velocity, just take a second to think about the word velocity. Velocity, speed. That's how quick something moves. How is that measured? If we think about the units, we have things like miles per hour, meters per second. It's a distance per time. Here, I have laid out the distance that this has followed. This string here that shows the distance it went, I can measure this. I have a defined distance, but how long did it take to roll through the well? Let's use some media magic here to time how long it took. So we know the distance that object moved, that planet moving past this star. We know how far it went. We can also determine how long it took to travel that distance. So if we take this distance, divide it by the time it took, we have the average speed that this object was moving as it moved by. This is a simplistic calculation, but it nonetheless goes to show, ignoring a number of other factors, it simplistically shows how quickly this marble needed to go to get away from the apple, how fast a planet or a satellite or a rocket would need to move to escape the sun, the earth, whatever. How quickly does it need to move to get away? What is its escape velocity? So here I've got my yarn laid out to show the distance that escaping object traveled. If I go all the way out here, unfortunately my tape measure is in inches. I will, to simplify things for you guys so you don't have extra stress on you, I'm going to go ahead and convert that and put it on the screen now. But it went out to about 58 inches. The distance that object, that escaping planet, whatever it may be, distance that it traveled was 58 inches. At this point, we finished the first portion of Part C. We have filled in the distance traveled, we have filled in the time elapsed, and we have calculated, by dividing that distance by the time, the escape velocity of the marble from the apple. But this next portion is asking us to think about black holes. I've got an apple in the middle. That marble apple here, it's pretty heavy. It's depressing the well significantly, but not as much as it could. Think about if I stood in the center of this thing. Think about if we plop a sumo wrestler in the middle of there. We take a marble, tiny marble, that weighs 100 pounds. That's going to be a really small dent in the gravitational well, but it's going to go very deep. If you have an extremely deep section of this gravitational well, what's going to happen? So a black hole, and we're going to have to run some thought experiments here because I don't have a 100-pound marble. I can't make this well infinitely deep without breaking my fabric. So I'll put up an image. Looking at the image, look at how deep this gravitational well is. Technically, a black hole has a massive, or a ton of mass concentrated into an infinitely small area called a singularity. The singularity is an infinitely small point in space that is collapsed down so far because all of the mass is being packed into one spot. So this singularity is making a massive depression in space-time. This well is extremely deep. Think about trying to get out of that well. Here I've got an apple that depresses the well reasonably, but it's not significantly deep. If this fabric was pulled infinitely deep to show this massive curvature in space-time, then we would try climbing out of that thing. Think of it as an actual well, like gravitational well. The apple, we got a well that's maybe like 6 feet deep. I might be able to jump and get out of that thing. But if it's a 100-foot well, you're going to need a ladder, you're going to need a lot of tools. What if that well goes all the way to the center of the earth? You're just not climbing out of that thing. That is what a black hole's gravitational well is. To escape an apple, to escape the gravitational well of a planet, or of a star, or of a galaxy, it's hard. They're pretty massive. They make significant dents in our gravitational well, but you still can climb out. Their escape velocities, as we increase the mass, they get higher and higher and higher and higher. They get harder and harder and harder and harder to get away from, but you still can. You can move fast enough to get out of this well. The thing about a black hole is that its escape velocity, the speed that you need to go to get away from it, to climb out of that well, is faster than the speed of light. The speed to get away from it is faster than the speed of light. The speed of light is the universal speed limit. No one goes faster than that. It is impossible. That's why it's a black hole. If to get away from this thing, you need to go faster than the speed of light, then it makes sense that it's black. Any light that goes close enough to this collapsed star, close enough to this singularity, it's not getting away. That's why in images of black holes, you will see that there's light bending around it, but there's a section in the center where that light just can't get away. You get close enough to that black hole, you're never getting away. That black line, that fringe where there's light and all of a sudden there's no light, that is the event horizon. Nothing gets away at that point. You have to go faster than the speed of light to get away. Take a second to look and read the misconception alert that I have plastered right into the middle of this lab. Pause now to read it. Black holes do not suck. They don't. It makes a lot of astrophysicists like super triggered if you say the word black holes suck things. They don't suck things into them. They have a massive gravitational well, so their ability to capture marbles rolling around, that is greatly increased. It is super easy to capture things in a gravitational well that massive, but it doesn't slurp it in. It doesn't suck it in. It's just capturing those materials. What's happening, what people are confusing for suck, is a concept called orbital decay. Orbital decay is listed in your lab here. Read through this if you haven't already and make sure that you understand the 3 components of orbital decay. There's more than just the 3, but these are the most basic. There are collisions with other materials. Imagine if I've got marbles rolling around at high speeds in this gravitational well. If they run into each other, they're going to slow each other down. So that's number 1. Number 2 is tidal forces. And 3, gravitational radiation. Gravitational radiation deals with gravitational waves. We're not going to worry about them too much. If you want to research it, please do. But it's just another way that energy is expelled as things move through space. So, number 4. Number 4 in part C of the lab. In the rubber sheet analogy, the rubber sheet being our trampoline here, we cannot make stable orbits because the marble or rolling objects are slowing down. If I roll a marble, it'll roll around for a reasonable amount of time. You'll notice that it's rolling and it's still going. And if we just keep watching, maybe fast forward here. It slowed down. Something took the speed away from this marble. It wanted to keep going, but something slowed it down. If it was able to keep up the same speed that I pushed it with, it would have just kept spiraling. So what slowed it down? What slowed down the marble in this analogy is friction. There is energy being diffused between the marble and the rubber sheet itself. This spandex is very low friction. But imagine I was using sandpaper here. If I was using sandpaper, you're going to really notice that friction as it rolls around this well. But if you take your hand and you rub it against the carpet, if you take your hand and you rub it against this, you start to feel heat transfer. That's evidence of this friction. So the marble is slowing down because of friction. But the thing is, space is a vacuum. It is totally empty. So things don't slow down. The Earth, in orbit around the sun, it's not going anywhere. It's not encountering some sort of surface. It's just moving freely through space, unobstructed by other things. So its orbit, it's been stable for 4.6 billion years. Number 5. Think about the Earth. The Earth itself is in a stable, unperturbed orbit around the sun. The International Space Station, on the other hand, is actually slowly spiraling down towards the Earth. Why would the International Space Station, being in space, be getting pulled down to the Earth? Feel free to pause and do some research or try to answer this question yourself. For number 5, what's making the ISS slow down? Why is it still, why is it falling down to the Earth? The thing about the ISS is it's actually in our atmosphere. It's in a very, very thin layer. It's in the exosphere. It's a very thin layer of the atmosphere, but nonetheless, there is an atmosphere. If you run really fast, you throw stuff, why does it slow down? It feels air resistance. That air resistance is technically all these little particles of gas bumping into us, slowing us down through collisions. So technically, number 1 in our orbital decay list is why the ISS slows down. Being in our atmosphere, it is encountering different atmospheric particles, different gases, as it goes around the Earth. And as it does that, it slows down a little bit with every single collision. They don't have to do it very often, but But there are videos online of the International Space Station doing a reboost, where it needs to speed itself back up to make sure that it doesn't fall down. Number 6 is a question with multiple parts, but we're going to think about the black holes. They've got extreme masses. They've got extremely deep gravitational wells, so they're hard to get away from. So think back to this analogy. If I have an infinitely deep hole, think about if I throw various marbles onto this fabric. It is going to be much harder to get away, and therefore, more materials are going to be stuck in the orbit. Take a second to try number 6 by yourself. It's talking about the gravitational well of black holes, an infinitely deep section of this trampoline. Try to answer the questions for number 6 by yourself, and we'll revisit in just a second. Go ahead and pause. If we were to throw a bunch of marbles in here at an infinitely deep well, something that's dragged way down, hardly anything is going to get away. But now think about it. If I take a whole bunch of marbles, and they're all getting stuck in this well, and again, I don't have this represented quite as well because there's so many, it's not as deep as what a black hole would be. But if I've got a bunch of marbles being slurped in from every direction, think about what they're going to do. They're going to collide. And if those marbles collide, they're losing horizontal speed. If they lose their horizontal speed, they're more likely to start to fall back down towards the black hole itself. So, black holes don't suck. They are just very good at causing orbital decay. If it captures a whole bunch of materials and those materials collide, then they erase their sideways velocity and they fall down. They would come together. If these are two objects stuck in orbit around a black hole, and they come together, coming in at fast speed sideways, exactly the same speed, let's say, they come in at exactly the same speed, they collide, lose their horizontal velocity, and fall downwards. So because black holes are so good at drawing materials in, that increases the number of collisions. And that causes things to slow down and start to slowly spiral into the black hole. Once it's sufficiently close, those tidal forces, oh man, it's just going to pull it in even better. So black holes, they don't suck. They're just very good at causing orbital decay. So with that, we've reached the final portion of the video. You now are on part 4 of the weekly activities. Part 4 is the closing. Through either the Google website, or the Google Classroom, excuse me, tinyurl.com/THS Astro. Follow that to find the quiz that everybody needs to take, or you can click or type in the link that I'm posting right here. Make sure that you've registered for the class using the code. If you have any other questions or concerns, please let me know. I will see you next week.